I welcome you all to this class of econometric methods. Myself, Dr. Imdadul Haq, is an associate professor at the Department of Economics in Aligarh Muslim University. We will now go to the realm of multiple linear regression. Like say, till now which we have discussed, conceptually it was a quantity demanded is a function of price, and we have a mathematical equation to denote it, that QD is equal to alpha minus beta P. But the question is, will it give a proper representation of the situation? Suppose we are taking that the quantity demanded of T. Now, have we taken the price of substitute? There may be other complements, like a cold drink can be a complement, substitute to tea. Even coffee is one of the best substitutes. Then have we taken into consideration the monthly income? Not only monthly income, there may be a person whose monthly income is very low, but he is from a very wealthy background, so his consumption level would be high. Have we taken into the taste and preferences, the season, what season it is, if it's a hot season or a cold season? So simple linear regression many a times will not serve the purpose. We definitely have to go for other variables. We have to add this. We have here in this, we have taken only one independent variable. We will be taking many more independent variables. And this is what is called as multiple linear regression. See, basically econometrics is an empirical estimation of causal relationship between variables. And in economic theory, we use an assumption ceteris paribus, which means other things remaining same. Like if somebody asks you what is the law of demand, you can simply say it gives an inverse relationship. If there is an increase in price, there will be a fall in the quantity demanded. But this is not the correct explanation of expression of the law of demand. The correct expression of law of demand is when price increases, quantity demanded decreases, comma, ceteris paribus. That is, other things remaining constant. For example, in the theory of demand, quantity demand is a function of price given the price of substitute goods, price of complementary goods, the income level, wealth, taste, and preferences. So, econometric analysis begins with the premise that if x and y are two variables representing some population, say price and quantity demanded, and say we are interested in explaining y in terms of x, then how can we be sure that we are capturing a ceteris paribus relationship? Like if we have just taken this expression y is equal to alpha plus beta x, what is the guarantee that we are measuring the effect of y on x keeping all other factors constant? When we regress y on x ignoring all other factors, the drawback of this simple linear regression is it will not satisfy the ceteris paribus relationship between x and y. So, herein, our aim is to study the relationship between x and y, but we have to consider three things over here: exact and inexact relationship. Since there is never an exact relationship between variables, how do we allow for other factors? Second, what is the functional exact, or the first point, exact or inexact, we have discussed in detail when we have in our earlier lectures where we discussed about mathematical economics and econometrics. The next thing is, what is the functional relationship? Is it linear or non-linear? Now, many things in real world, like your cost curve. If you remember your cost curve, your cost curve is something like this. Not only cost curve, your Kuznets curve. They are all they are not of this form, they are not linear, neither like this nor like this, rather the relationship is like this, a curve can be like this. So if this is the form and we are taking this form, then we are doing something wrong. Our model is not properly specified. And the third thing is, how can we be sure that we are capturing a ceteris paribus relationship? So, see, even if we are interested in studying only one independent variable, even if we are interested in just taking the effect of one variable x1, we still need to introduce all the variables. Then only we can have this ceteris paribus relationship. So, we can define multiple regression. Mathematically, we say y is a function of x1 and x2, and then we can say that y1 is equal to b naught plus beta b1 x1 I plus x b2 x2 I. So, here we extend the simple linear regression model to study the relationship of two explanatory variables. Let us take the economic theory of demand. Economic theory postulates that the quantity demanded of a given commodity depends upon its price and the consumer's income. So now we have y is equal to f, x1 and x2. Now, as the theory does not specify the mathematical form of the demand function, we assume a linear relationship. We can say it like this: yi is equal to beta naught plus b1 x1 plus b2 x2. Now, there is an exact relationship whose meaning is that the variation in the quantity demanded are fully explained by the changes happening in price and income. Now, so the first part, if you can see that the part from beta naught plus beta 1 x1 I plus b2 x2 I is your systematic component, and the second part is your ui is your random component. So, however, if we gather observations on these variables during a certain period of time and plot them on a diagram, we will observe that not all of them lie on the same plane. Some will lie on it, some will lie above it, some will lie below it. This scatter is due to the various factors omitted from the function. The influence of such factors is taken into account by this random component, that is ui. Now, next we go by the assumptions of multiple linear regression. Here almost the assumptions of a simple linear regression model where it was only one independent variable was there, the same assumptions are repeated and one is added, that is, there is no relationship between two independent variables. So, what are the assumptions? A quick recap: the error term is random, it can assume any value, it doesn't, and the error term has a mean value, has a zero mean value for each x. Then the third one, the variance of each error term is the same for all the x values. Fourth, the error term is normally distributed. Next is the error terms are not correlated, that is, the expected value of ui uj, error in one period with the error in other period, is equal to 0. The error terms are independent of the explanatory variable, that is, the expected value of ei with x1 is 0, and since we are assuming two variables, so again the expected value of ui with x2I is also equal to 0. It is because the values of x are fixed. If you as we have seen earlier in our example of income and consumption expenditure. There are no errors in measurement. This assumption was also there in your simple linear, and I just at the moment leave 8. At the moment I just leave 8, and then I jump to question number 9, the assumption number 9, that is we assume that there is a correct aggregation of the macroeconomic variables, and then we have also assumed that the relationship is identified and the model is correctly specified. Now we move to this one. This is an addition. What it says, there is no perfect linear correlation between the independent variables. This thing was non-existent in the simple linear regression because there was only one independent variable. But if there are more than one, if two or more than two independent variables are there, and these independent variables are linearly related with each other, then it happens that then there will be a problem, and that problem is called as multicollinearity. So basically, we have just done a quick recap of the assumptions. These assumptions are the same as a simple linear regression model, which we had done in detail, except a new assumption is that there is no perfect linear correlation between the independent variables. Now, we are going to derive the values of beta 1, beta 2 and beta 0, the intercept term and the first regression slip coefficient beta b1, second regression coefficient b2. I may sometimes say in place of b, I may sometimes say beta, so just ignore it at the moment. So now we have this multiple linear regression form, that is yi hat is equal to b naught hat plus b1 x1 plus b2 x2. So if you take the error term, what is the error? Error is yi minus yi hat. Now this error, we can write it like this based on our earlier logic, because we know what we just write yi as yi, and yi you write this, the entire thing you put it over here. The sign has changed because here there is a minus sign. So now we have the function which is summation e square is equal to summation bracket open yi minus b naught minus b1 hat minus x minus, sorry, there is no minus sign over here. It is b1 hat x1 minus b2 hat x2. Please ignore this minus sign over here. That's a mistake. So now we have to minimize. Now what we are supposed to do, we are going to minimize this above equation so that we can find the values of beta naught, beta 1 and beta 2 which minimize this error term. That is, we are going by the same method where we are minimizing the error as we have done in the simple linear regression model. So now when we do the partial differentiation of this equation with terms of beta naught, so we get delta summation yi minus b naught minus b1 b naught hat minus b1 hat x1i minus b2 hat x2i whole square divided by delta beta naught or b naught. Next we do the partial derivative of the same equation with respect to beta 1, so we get delta summation bracket open yi minus b naught hat minus b1 hat x1i minus b2 hat x2i raised to the power 2 and next time divided by delta beta 1 hat. Next time we do, again we partially do the partial derivation of this with respect to beta 2 hat, so we get delta summation bracket open yi minus b naught hat minus b1 hat x1i minus b2 hat x2i the whole square divided by delta beta naught, and all these we equate to 0. Now we take individually each one of them. Say first we take the partial derivative done with respect to beta naught. This equation can be written as 2 minus 2 bracket open yi minus b naught hat minus b1 hat x1i minus b2 hat x2i is equal to, we equate it to 0. Now we divide both sides by 2, this also and this also. So what is left is, this is 0. So the minus signs, this 2 disappears. We divide, and then also we divide it by, sorry, minus 2, not exactly by 2, by minus 2. So minus 2 cancels. This side there is no change, this is 0. So yi minus b naught hat minus b1 hat x1I minus b2 hat x2I is equal to 0. We do a rearranging. We take all the terms except yi to the right hand side, and we also do the summation. Upon doing this, we get summation y is equal to, because since beta naught is a constant, we get n b naught hat plus b1 hat summation x1I plus b2 hat summation is also there, b2 hat summation x2I. So this equation, we will be trying to get 3 different equations. So this is the first equation which we have got upon doing the partial differentiation of the error term with respect to b naught. Next, we do the partial differentiation of the same equation with respect to b1. This is b1 now. So upon doing that, what we get the value as minus 2 summation x1I bracket open yi minus b naught hat minus b1 hat x1I minus b2 hat x2I. This is equal to 0. Now what we do, again we simply divide both sides by 2. So this 2 vanishes. Next, what is, we open the brackets. When we open the bracket, we can write it as like this, x1I yi, then this multiplied by this x1I b naught, then x1 b1 hat x1 square, because all this is also x1 and this is also x1, and next time it is b2 x1I multiplied by x2I. So we get this equation. Now we try to write this equation in the term of this. So we take all the other values except for x1I yi to the right hand side. So finally we get the second normal equation, which reads as x1I yi is equal to beta naught hat summation x1I plus beta 1 hat b1 hat summation x2 1I plus b2 hat x1I x2I. So this was the second normal equation. Then we move to the third equation. We move to the derivation of the third equation, which can be said to be as we differentiate the error summation of error equation by b2. So what we get is minus 2 summation x2I yi minus b naught hat minus b1 hat x1I minus b2 hat x2I is equal to 0. This, when we divide both the sides by minus 2, we get rid of the 2 over here and the minus sign. So what is left is, what we do, we divide both sides by minus 2. Now then what is left is x2I yi. When you open the bracket, it becomes x2I yi minus beta naught b naught hat x21 plus b1 hat x1 x11 x1I x21 minus b2 hat x2 summation. I missed the summation sign over here. So just again rearranging, we take all these terms to the right hand side. Upon taking all these terms to the right hand side, we get the third normal equation as x2I yi is equal to b naught hat summation x2I plus b1 hat summation x1I x2I minus b2 hat, we get, no, this will be plus, it will plus, please ignore it, and it should be plus b2 hat summation x2 square. So this we can write all as these are the three normal equations which we have derived by partial differentiation, first with of the by partial differentiation of this equation, the partial differentiation of this equation first with respect to beta 1 or b1, then with respect to b2, and then with respect to b3. Now we take the first equation, or we stop here. In our next class, we will start from here, that we will work on with these normal equations and try to find the value of b1 hat, b2 hat, and b0 hat. Thank you.